Hi, I'm Viritha Kaza. I work for General Motors as a data scientist in Vehicle Safety Analytics Group. I started at GM in 2014 when our CEO, Mary Barra, announced that a new safety analytics team would be started. My initial assignment was to develop data analytics framework to identify potential safety issues by mining every source of data available to us, such as voice of customer, warranty, social media, and so forth, and submit any identified potential safety issue to recall decision-making groups that act swiftly. Since then, I have been involved in various vehicle safety data analytics projects that provided insights and foresights to various engineering groups. Prior to my GM experience, I worked as a bioinformatist at the University of Michigan, which focused on developing data analytics toolsets to identify detected genes and their pathways. This experience helped me to create novel data analytics methods to identify potential safety issues. I started with few programming languages, but as GM entered the world of big data, I've been exposed to many more new technologies in the analytics space. We all know that we are fast approaching a new era of the data age. From autonomous cars to Industry 4.0, the world we live is undergoing a fundamental change, especially transforming the way we live, work, and entertain. And data has become critical to enable these transformations. Mere access to this data is not enough to unlock valuable insights and foresights hidden in these vast amounts of data that can transform businesses or societies. So we need a toolkit like data analytics to unlock the power of data. Today, I'm going to touch a little bit on how we can unlock the power of data using the data analytics and various exciting opportunities in this field. And in the later part of my presentation, I can show how we can get insights and foresights from a data set, and mostly how fun it is to code and understand hidden patterns. We at General Motors are driven by our vision 3 zeros. That is to strive to achieve zero crashes, zero emissions, and zero congestion, and make this world a better place. Data analytics is enabling to realize this vision and guides us to make better decisions to achieve this feat. There are several questions that arise in everyday work streams or at instances to narrate a big idea or potential solution sets to burning business questions. In these kinds of instances, most businesses these days use data analytics to examine their data and convert them into insightful information that creates knowledge and ultimately help organizations to make better, more informed business decisions. There are different forms of data analytics we use to answer different questions. That brings us to the data analytics maturity curve illustrated by Gartner. This curve depicts various stages of data analytics on a value complexity curve. Descriptive analytics that provide insights on what happened in the past, example, summarizing past data, usually in the form of charts or dashboards. Diagnostic analytics that can answer why did it happen, example, to find the root cause of problems associated with vehicles or business processes. Predictive analytics that can tell what will likely happen in the future, example, identifying emerging issues or business trends. Prescriptive analytics for how we can make it happen. For instance, either a product strategy or a marketing strategy. Combining everything to determine the course of action to take in the current problem. Using AI to study large amounts of data, communicate decisions, and even put those decisions into action. The complexity of these data analytics stages increases as we grow from descriptive to prescriptive. But the business value also increases. Organizations such as GM uses all forms of these analytics at various stages of product development or for developing business strategies or for day-to-day business activities depending on the needs of the business. Depending on the skill sets, there are several job opportunities at various stages of analytics as shown on this chart, such as data analyst and business analyst, etc. In the descriptive stage, roles like business intelligence and data storyteller at diagnostic analytics stage, data miner, data scientist, machine learning engineer helping in generating foresight at predictive and prescriptive analytics stages. I'm going to talk about some of these roles and responsibilities on the next slide. As mentioned earlier, job opportunities span across the stages of data analytics depending on the skill sets required for each of these roles listed in here. For example, business analysis. This role drives organizational initiatives around business analytics, big data, and cloud solutions, data warehousing. It includes work related to strategy, roadmap, critical metric definition, reporting, and dashboards. Continuously enable to new solution trends. Business intelligence. This role involves collaboration with business, IT, and analytics community to capture, prioritize, and document data analytic requirements and drive measurable results. Provide recommended types of reporting analytics and procedures to apply to meet stated business objectives. Prepare analytical reports that effectively summarize results, assumptions, and conclusions. Data analysis. Develop POCs and work with other teams like IT department to productionize efforts into a robust, scalable solution. It also involves generating ongoing, actionable new insights and educating various groups on things that they do not know. This role can also function as a project manager and business relationship liaison with other groups. Data science. Build predictive models and machine learning algorithms and undertake pre-processing of structured and unstructured data. Monitor and sustain model effectiveness and present complex information using data visualization techniques. Proficient in one or more analytical methodologies such as numerical optimization, econometric modeling, and forecasting, machine learning, and text analytics. Decision and data science researcher. Develop innovation roadmaps for areas of decision and data-centric analytics that enable game-changing capabilities for GM. Lead research and or experiments to collect required data and validate research ideas in developing. Execute technical programs and coordinate with various functions of the innovation process as required and act as a mentor to junior technical staff and innovation teams. Prospective career seekers can start at any stage of data analytics and move to other roles by enhancing skills in any of these categories. For instance, one can start as a data analyst and take up data scientist role by acquiring skills in data modeling and machine learning techniques, which will allow to contribute solving complex business problems. Based on my experience as a data scientist, I can certainly say that career opportunities in data analytics are both rewarding and satisfying to have a meaningful career path. Now, let me show how we can have fun in coding. Let's unlock the power of data with this tutorial. This Jupyter tutorial notebook is for beginners. This notebook was built using an inbuilt toy dataset to help demonstrate some exploratory data analysis, determine which model you might select for your data, and shows you how to use and evaluate your model. In Datathon events, you are provided a data set and are required to develop a machine learning model which can automate the prediction of the data. But beyond just making predictions, we have to determine if the model performed well and to explore what features drive the distinction in the target. Often, you're building, testing, and comparing the results of multiple prediction models to determine which model will provide the best predictive performance. In this tutorial, I'll be explaining the differences between linear and logistic regressions and focusing on employing and evaluating a simple linear regression model. Now let's know some background about regression. Regression models show the relationship between variables by fitting a line to the observed data. Based on that line of best fit, we can then estimate how the dependent variable may change when one or more independent variable change. Two of the most commonly used regression models are linear regression and logistic regression. Linear regression models use a straight line of best fit, while logistic regression model use a curved line called the sigmoid curve. Now let's see the difference between these two. Linear regression models are used to predict a relationship between continuous dependent variables from independent numeric variables. We use linear regression when seeking to answer questions like, does age impact blood pressure, and if so, by how much? Or does insulating my house reduce my heating costs, and if so, by how much? Logistic regression is used where the target variable is categorical data or a qualitative data set. Example, gender, eye color, favorite sport, zip code, yes or no responses, etc. are all the categorical data variable. For example, the probability that a customer will purchase a home or a patient will have an adverse reaction to a drug are some of these examples. In short, linear regression is for continuous variable prediction, while logistic regression for categorical variable prediction. Now, let's see the relationship between these variables. There are two important terms which come in handy. One is covariance, a measure of how the two values covary. In other terms, measures the directional relationship between the movements of two random variables, whether positive or negative. Correlation is to describe linear relationships between two variables. We use correlation, which measures the strength and the direction of an association between variables. One of the most common errors in statistics is assuming that when there is a correlation, then it causes the other, which may not be true. That is, if X is correlated to Y, then we cannot conclude that X causes Y. Now, let's put this into practice. Let's first import the packages that we require, that is NumPy, Pandas, Matplotlib, and Seaborn, which is also based on the Matplotlib, which is used for visualization, and stats and stats model from SciPy. Also, the train test to create our train test split data sets, we use train test split from sklearn model selection. And to scale our data, we use standard scalar or min-max scalar from sklearn preprocessing package. And to import our model, we use linear regression from sklearn linear model. Now let's execute this. So now I have imported the packages that I require. Now let's see the linear regression assumptions. When fitting the linear regression model, we make the following assumptions. That is, there is a linear relationship between the dependent and independent variables. Next, the independent variables are independent of each other. That is, there is no multicollinearity between the independent variables, and residuals are normally distributed. And last, the variance of error terms are similar across the values of the independent variables, which is called as homoscedasticity. The first two of these assumptions are checked before the model is fit, while the last two are checked after the model is fit. This is a process called the performing model diagnostics. Now, let's see the steps for fitting the linear regression model. So first, we check the data if appropriate and see the underlying assumptions by using a distribution of independent variables or seeing the relation by correlations or multicollinearity. Then we split the data into train and test sets and instantiate and fit the model. And finally, we evaluate the model and perform model diagnostics like R-square or residual analysis. Now, let's import our inbuilt toy dataset, which is the California housing, from sklearn datasets, and I'm executing this. Suppose you get an error, got an unexpected keyword argument. That means your version of sklearn has to be updated. Now, let me see some description about our dataset. I use DSCR for this because we get much more information about it, more than info statement, where in info statement you get just the column names and data types. But this DSCR gives us more information. So let's see the California housing dataset. Here we see that there are 20,640 rows of data, and there are 8 attributes which are all numeric. We see two kinds of data here. Some are specific to the block, while others are household. We see the median income, house value, population, latitude and longitude, which are specific to the block. And a block is basically a group typically consists of a population of around 600 to 3,000 people. And note, this is an US Census data for California in the year 1990. Also note that there is another group which is average rooms, average bedrooms, average occupancy, that is the average number of household members. So a household is basically a group of people residing within a home. Now, we also see that there are no missing values here. If there are missing values or null values in your data set, and if your data set is very large with very few missing values, you could ignore them. But if you don't want to do that, then you could replace it with the median values at the missing location, or you could also use other impute methods to fill in the missing values. Now, we saw more about our data set. Now let's merge both the target, that is the house value, and the rest of the data features, that is other 8 attributes that we have here in this step by using concat, and let's see how the data frame looks like. Now, as you can see, there are 20,640 rows, but now we have 9 columns. So we have the median house value also included in our data set. Now that's good. So let's see our data distribution and some more statistics from our data set. So first I'm plotting a histogram with 30 bins, that is 30 buckets, with the figure size of 20 by 15, and let's see this plot. So here we see that the median income is a distribution with a long tail. It means that the salary of the people is more or less uniform, normally distributed, but there are some people getting a very high salary. Regarding the house value, house age, the distribution is more or less uniform. Now let's see our target variable. The target distribution, that is the median house value, has a long tail as well. In addition, we have a threshold effect for high valued houses. All houses with a price above 5 are given the value of 5. Here we see for the latitude and longitude seems like a bimodal distribution in our data. Focusing on average rooms, average bedrooms, population, average occupancy, we see a range of data is large with unnoticeable bins for the largest values. It means that there are very few with very high values, which could be considered as an outlier. Let us see that from more basic statistics that we can see from our data set. Now let's use describe to get some basic statistics. So here we see that there is a count of 20,640, which was our data set. We have mean, standard deviation, min, 25 percentile, 50 and 75 percentiles, and max values. Here we can see that those 4 attributes which we spoke, average rooms, average bedrooms, population, and average occupancy, have a max value which is way beyond our 75 percentile values, which indicates that these could be outliers. Now, checking the relationship between these variables. Using a reg plot, I'm trying to see the relationship between the median income and median house value. Here we can see it is positively correlated, and which is strong. Now let's see the relationship between population and median house value using the same reg plot. And now we can see that it is slightly negatively correlated. That means as population increases, the median house value will slightly decrease. Now let's see the correlation between all the variables using the core and using the heat map to see the correlation between these variables. And now you can see that median income and median house value has a good positive correlation, and the population is slightly negative. But here you can also see that average bedrooms and average rooms have a strong positive correlation between them. And also we observe that the latitude and longitude also have a strong negative correlation, which is against our assumption that these independent variables should not be correlated, which is multicollinearity that is observed here. But there are a few solutions to address this multicollinearity. One is to remove some of these highly correlated independent variables. So we can either remove average rooms or average bedrooms from one of them from this set, while we could remove a latitude or longitude from this data set. Or there's another method which you could do is we could linearly combine the independent variables, such as adding them together and then doing the analysis. Or we could perform an analysis which is designed for highly correlated variables, such as the principal component analysis or partial least square regression. There are other advanced forms of regression analysis like lasso or ridge regression that can handle multicollinearity as well. For this part, I'm not eliminating any of these these attributes, but I'm using the ordinary least square method to do a predictive model. And let's see the summary of this data. Here, you can see that the R square value is 0.606, which means that it is 60.6% of median house value could be explained by these attributes. Now, we can see that the probability F statistic is closer to 0, which is also a good sign. There are two important things that you could see in this data set, which is coefficient and p-values. This coefficient represents the mean increase of median house value for every additional 1 unit change in the attribute. Another important factor is that p-values. So p-values determine if all the attributes are significantly contributing to the median house value. If p-value is closer to 0, that means they are significantly contributing to the median house value. If p-value is greater than 0.05, which suggests that the changes in the predictor are not associated with the changes in the response. That is, the population here is not significantly contributing to the median house values. We also observe that there is a large condition number here. This could be addressed by pre-processing the data using scaling. Another problem is we use the entire data set to train our model. We haven't seen how this model would perform with the unseen data. Let's make it right later on when we are processing this data. So now let's see the scatter plot for this model that we fit by seeing the actual versus the predicted median house values. Here, we also observe that the median house value seems to be scaled, and we could use some best estimation for each of these, including the median income, to be more realistic values for California housing, and during those time frames of 90s, because this data set was census data for 90s. So now we are scaling the median income and median house value to more appropriate estimates by multiplying it with 100K for median house value and median income by 10,000. And we can see using the head statement, which provides you the first few data set records. And here, now you can see a little more realistic values. Now let's see the data processing. So we have to split the data. Here we are splitting it with X being all the attributes, and dropping this median house value because we are trying to predict this one, and Y, which is the median house value. Now let's see both the shapes of the X and Y data frames here. We see that it has 20,640 and 8 attributes. So the 8 attributes are all the independent variables that we are considering. And the other Y, which has just the median house value for with 20,640 records. Now let's split the data into training and test data sets. Using the train test split with the test size of 0.2, which means 20% of it is what we are considering for the test data set, while the rest 80 as the training data set. Note that we also are considering the random state so that we could repeat, whenever we repeat this process, we would get the same data sets again. Now, let's see the shape of our training and test data sets. So we see there's 20% split that between the test and the training data set. Now let's scale the data. This is one of the pre-processing steps. And to scale the data, I'm trying to use the standard scalar method, which is the industry go-to method, where the data is arranged into a standard normal distribution with a mean approximately equal to 0 and the standard deviation of 1. So here we are using that selected scalar, which is the standard scalar method, and fitting for both the training and the test data set. Now, the next step is to fit the linear regression model. We are already imported this, but I'm just trying to show that we are doing it for linear regression from the linear model here. And also we are importing the R-square score from sklearn metrics. And then we are instantiating a linear regression model here, and by fitting for the training data set and predicting for the test data set. And here we are trying to get the R-square value, which is the coefficient of determination or the percentage of variance explained by the model. So now let's execute this one, and we get a score of 0.6, which was similar to what we had got in the ordinary least square method as well, which is 60%. Now, we also saw that there were outliers before. So let's see if we can improve our score by removing these outliers. You should always note that sometimes removing the outliers is not a good thing to improve the model, because these outliers could be an influential data points in our data set. So sometimes it's not recommended, but depending on your need, you could do that. I'm trying to employ an automated outlier detection method here using local outlier factor, and from the sklearn neighbors method using the local outlier factor But one thing which is important to realize is local outlier factor is sensitive to number of dimensions. If we have more features or attributes that we are considering for the model, it becomes less reliable. So we should keep that in mind when we are using the local outlier factor. And I'm using the contamination of 0.01 with the neighbors of 20 and running this one to fit the local outlier factor into our training data set. And we are selecting all the rows that are not outliers here. So that is applied to our training data set so that we can have all the outliers removed. And we can see the shape of our outliers here. I mean, after removing the outliers, and then we can instantiate a linear regression model where we are fitting the training data set after removing the outliers and then predicting it. And here we can see the R score value of this one. So it has increased slightly, which is from 60 to 63%. It has the R score value has increased, which is good. Now let's check the last two assumptions that we had for our linear regression, which is the residuals are normally distributed. Here, the residuals are calculated by the difference between the predicted values with the test data set values using a disk plot. And let's see how the graph looks like. So it does show a normal distribution for the residuals, which is good. Now, let's see the last assumption that we had, which was homoscedasticity in our data set, that is equal variance for all the independent variables. Now, to do this, I'm just creating a data set for residuals and ypred so that I don't get an error for scatter plot, so that I can mention it x and y values here. And now let's check how this graph would look like. So here, if there is a definitive pattern like linear or a funnel shaped obtained from this scatter plot, then heteroscedasticity is present. If graphically you're not very clear if there is homoscedasticity or not, then you can use test statistically to check the homoscedasticity. But if we do observe heteroscedasticity in our data set, then we can also overcome this problem by using weighted least square to overcome this problem by dividing the equation by the standard deviation when you know that. So there's always a solution to do that as well. So here we have seen how to build a linear regression model, how to evaluate our model using R square. You could also do other metrics like root mean square analysis, etc., to see how our model is performing. And then we have already also checked the assumptions behind our linear regression model and what are the solutions if any of these things fail. Now, let's see the final takeaways from this tutorial. There are many more models outside linear and logistic regression, like ridge or like lasso regression. All these are there are various models, but the key is to know why and when to employ each one based on the data you have and the problem you're trying to solve. Thank you.